Welcome to the channel, ladies and gentlemen. We will be talking about how airplanes generate lift today. And very quickly, the reason I'm doing this video is actually it dawned on me that I'd never addressed this and that it might be kind of interesting because, well, a couple of years ago I stumbled on an article or a blog or something like that written by a guy that did a really good job of explaining some of the more complex uh, issues revolving around the principles of flight. And and one of the articles was about how airplanes generate lift and how it is um, taught incorrectly in a lot of places, and it's very commonly taught incorrectly. I don't know if that sentence is correct or not, but anyway, so it just sort of dawned on me that I'd never addressed this, and that it was something that was really interesting to me. So what's interesting about science and physics and things like that, to me, is that I know that we think oftentimes that science has pretty much shown us exactly how something works, and then later we find out that we didn't really know, or that we have a better understanding at a later date because we've discovered something new. And as far as how airplanes generate lift, I think it's pretty clear that the experts know what works, but there seems to be a lot of conflict on exactly how it works. So that's not to say that the principles are wrong. It's just that I think that it's very complex. And so the two major theories that I know of, which are Bernoulli's principle, um, which is often called different things like longer path theory or something like that. I can't remember all the names of it. And then just the theory of creating downwash, and I don't know exactly what that theory is called either. It's probably called a bunch of different things. But those are the two that I know of, and they both seem to have a lot of credibility and credence. But really, as far as basics go, Bernoulli's principle is the only thing that we're ever taught in physics until you get into some higher level stuff. And you know, you might learn other things in college, certainly if you're taking physics classes in college and things like that. But at a basic level, most people, and I've even argued with, I have literally argued with people who were in the Air Force and people who were mechanics on airplanes for major companies that do a lot of work on airplanes. And they would argue with me about how it's just Bernoulli's principle and that's it. And of course, there's some really big problems with that we'll talk about here in a minute. Um, but my intention here isn't to say, oh, I got you, you're wrong. My intention here is to say that it's more complex than just that. So Bernoulli's principle, I think, as far as I know, I'm a hobbyist. I don't know, I'm not an expert, but Bernoulli's principle seems to have an effect. I can't see how it wouldn't. But there's more to it than just an airfoil and air going faster over the top than the bottom. So what we're going to do is I'm going to pause it, first of all, so that it's quiet, and second of all, so that we can see. And the A-10 may not have been the best aircraft to look at, but we're gonna try here. That zoom is really fast when I'm in this mode, I guess. But obviously you can see that it's curved over the top, and it all the way down the wing, the length of the wing. Um, it's curved. Now the airfoil changes from the root to the tip, but you can see it's also a little bit curved on the bottom, but it's quite a bit flatter on the bottom than on the top. Okay, and that's very important because according to Bernoulli's principle, the air, and everybody knows this, but the air goes um, has to travel further over the top than over the bottom. And that makes it go faster. It makes it have lower pressure on the top and higher pressure on the bottom, and that generates lift. That's the idea, obviously. And you can see here on the back, the flaps are kind of curved down to push air down, and that's the other principle, is that we need to push air down to generate lift as well. So, you know, again, that's not necessarily the easiest way to see it, but here in DCS, that does, you can kind of see it. So we're going to fly upside down for a minute, and I'm going to try to find the horizon there. Now, I can't fly upside down forever because it'll starve out of fuel, but you notice that I am flying upside down. There, I think we were starving right there. So if we look though now, the curved portion is facing up, and the faster air is on the bottom. And this is the big argument that I think gets people to thinking about this. How do airplanes fly upside down if it's just Bernoulli's principle? And that's the question. So that should really get you thinking, like, how can this aircraft fly upside down like that? And interestingly enough, you've got about 10 seconds worth of fuel, and then your engine shut off, and I ran into it. Now there is an engine startup procedure that I would go through, but I don't. That's not the point of the video, and I don't care to. So we're going to switch to a different plane, and we'll talk about this a little bit more real quick. Okay, so here we are in the P-51 Mustang, and I'm going to try to fly straight and level, but I'm also not really paying attention to my gauges while I talk, so it may not happen. But the P-51 is famous because it has a little bit of a different airfoil. And again, the airfoil, I'll get kind of level, and then we'll just pause it. The airfoil changes from root to wingtip, but it's kind of supposedly it's the same on the top and bottom. Now, I don't think it's exactly the same on the top and bottom, but as you can see, it's pretty similar. It's also it also gets to its thickest point further back than normal, which is one of the big breakthroughs on it. So, but the idea is that it's really, really close to being the same on top and bottom, and you can kind of see that here. So if that's the case, then the longer path theory isn't quite enough to explain this. Now, of course, we're not generating a ton of downwash, it looks like, there either. So maybe that's not enough to explain the theory. I don't know. Let's go ahead and unpause it here. And once again, I'll I'll roll it over. And I don't fly this plane much, so whoops. And this one will shut off also. Put the wrong kind of G on it there. So we'll pause it. We'll look off to the side. Whoops. I gotta back out here. There we go. My head tracking and all that gets really weird sometimes. Consequently, if anybody knows about the way they've started doing the spec layers on the P-51, let me know. I've redone all the spec layers on this thing, and I can't get it all to be shiny the way I want. So as you can see, my nose is high here, and that's kind of the point. Is I'm having to generate lift by it's really angle of attack is what I'm getting at here. As we learn, angle of attack matters, and the wing angle or the angle of incidence is not the same as the, I guess, line of sight path of the airplane. And I'm not necessarily using the correct terms. You can use a bunch of different terms on this, and I could probably do a better job of explaining it. But the path that the airplane is traveling is not necessarily the same as the angle of the wing, and that's important. You can watch a lot of old, like World War II training videos. There's one in particular about a B-17 that sort of discusses this because I'm going to pause my head tracking. So that was weird. And in this video, it sort of highlights the angle of attack issue because the instructor is telling the pilot, and I don't know that this is necessarily the best way to do it, but he's telling the pilot, if you keep the tail wheel down, you might be able to take off in a shorter distance. And the young pilot is saying, well, don't I have the extra drag on the tail wheel? And the instructor says, yes, but your but your angle of attack is generating more lift. Of course, it's also closer to a stall, I think, as well. So, and when you're going slow, maybe that's a bad thing. But that was a trade-off. They did a good job of discussing the trade-off between the extra drag from the tail wheel and the angle of attack being more conducive to generating lift. And he was basically saying that, yes, you'll take a little bit longer to speed up because of the drag, but you'll be able to take off at a lower speed than you would if you brought the tail wheel up and put the angle of attack more in line with the ground level, so to speak. So anyway, my nose is high, and I think that whenever you're flying upside down in a plane like this, you generally have to, so that you can provide downward force with the air, and that would provide an equal and opposite force on the airplane itself, if that makes sense. So, and that's literally the idea that I'm getting at here, is that you have to generate lift, and yes, the longer path theory works to some degree. It certainly has an effect on the flight of the airplane, and it definitely has an effect on the lift, but it's not enough to explain it all. And also, for that matter, I personally think, and again, I'm a hobbyist, I'm not an expert, but I personally think that the downforce generated by just pushing masses of air down is a better explanation of how aircraft can fly and generate lift than Bernoulli's principle. So, and the reason is because I think it's pretty clear that downwash is a thing, and it's a very, very important thing. So, you'll hear stories about small aircraft coming in behind big commercial airlines at airports, and they will be affected by the downwash. Ground effect is a thing. Helicopters use it as well. So I just think it's very, very clear that mass of air coming down from the wing is very, very, very vital to lifting the aircraft up. And it's not taught very much, certainly not on a basic level. Whenever we're talking about lift in schools and things like that, it's really not. They kind of don't even get that far. Maybe it's because that's just not the point of of physics in school. I don't know, but there we go. That it's more complex than what we've made it, and it's more complex than most people think. And there's a lot of people even in the industries associated with flight that don't know anything but Bernoulli's principle, and that's a shame because it's actually a lot cooler than that. Complex things are cool, and cool things are often complex. And I think that the more you know, the better off you are. And so there you have it. Now I'm just going to fly around just for fun.